Hi, my name is Thomas Higdon. I'm a software engineer on the team that builds live streaming video infrastructure at Meta. I've been here for nearly 5 years, working mainly in this area. I've worked on other video systems in the past at other companies like Akamai, but I found myself at Meta working on interesting problems that impact millions or even billions of people. I'm passionate about optimizing distributed infrastructure to deliver live media efficiently and reliably. Today, with my colleague Jordi, we'll present a project we built to improve the reliability of our live stream ingest video systems over long-haul backbone networks. Here's our agenda today. I'll present the introduction and motivation, and Jordi will present the proposal and results. At the end, I'll discuss the conclusions. Now let me introduce some important aspects related to our team. The technology we build is part of Meta's video org. We build the tech stack that powers Facebook Live and Instagram Live. We support video that is ingested from first-party broadcasters, our family of apps, using an in-house video protocol. But we also support third-party broadcast softwares and hardware, like OBS, Browser Clearcaster, and Elemental via standard protocols. Let me now give you a few important data points related to scale that will help in understanding this project. Our systems ingest several million live streams per day. The size of these streams ranges from a UEFA Champions League final with 7 million viewers to, for instance, me broadcasting myself on vacation to a few friends. Regardless of the audience size, though, we want excellent reliability. Our live streams are ingested via one of 100 plus points of presence, or POPs, all around the world. And from there, they are routed to one of several Meta data centers all around the world. Most of our infrastructure is built in-house. This includes software, servers, switches, a CDN. This is all built by Meta. The complete ownership of such infrastructure gives us a unique opportunity to innovate. Allow me to quickly talk about the most important part of the project, the people involved. This has been a big cross-functional project across a number of teams at Meta. I want to recognize the contributions that this exceptional group of people have made to this project. What is Oil Vcache, you might be wondering? We'll get to that later. So let's dig a little deeper into the technical stuff. Here is a block diagram of our live streaming ingest infrastructure. We use two different application protocols for ingest, RTMPS, which many people may know for third-party encoders, but also Rush, our in-house quick-based ingest video protocol, which we use for our first-party encoders. In fact, we've recently published an IETF draft proposal for standardizing this protocol. From the encoder, our global load balancing systems route the stream to the nearest POP that can handle the traffic. The transport protocol, whether it is TCP for RTMPS or QUIC for Rush, is terminated on a proxy on the POP, which then routes the stream by creating another transport connection to an appropriate data center and tunneling the video data there. In the data center, the stream is transcoded and then distributed to the viewers. This is what we call the legacy path today. So what is the motivation for this project? So let's go back to the block diagram. Internet user contribution into the POP is challenging due to less reliable internet networks and changing bandwidth conditions on last mile links. We optimize the reliability for this hop by doing ABR and making data-driven client-to-POP routing decisions that minimize latency and maximize bandwidth. These measures cover the client-to-POP path well enough, but we still need to route from the POP to the data center. In Meta's original live stream design, we assumed that the backbone network hop would be performant and reliable at all times. That turns out to be close to the truth, but there are certainly some nuances. Our network and traffic infrastructure is multi-tenant, and in fact, Livestream is a relatively small share of such traffic within the overall Meta ecosystem. The vast majority of requests at Meta are short-lived HTTP requests that generally last much less than 1 second. If such a request fails or times out, for example because a particular network link has failed, then it's easy for the application to retry it without much penalty to any user experience. In fact, on such a retry, it's very likely that it will be routed via a different network link and have a high probability of succeeding. This overall network design is optimized for such short-lived, retryable requests. Live streaming is different though. RTMPS and even Rush over Quick depend on a long-lived connection. This long-lived connection requires a constant, steady stream of multiple megabits per second over a long period of time. 8 hours is the typical maximum length for Facebook Live broadcasts. This long-lived connection follows a chain of physical network links, switches, routers, and proxies. Any single issue with any of these components during an 8-hour-long broadcast would cause disruption to viewers. Depending on the type of failure, it will either cause buffering and delay, or a transport disconnection that is propagated back to the encoder, which must then reconnect. Either way, this will result in a disruption to the viewers of the broadcast who are viewing it in real time. And in fact, we do see these types of issues in our network regularly enough that it violates our reliability service level objectives. For instance, we had a situation where an individual group of proxy hosts were overloaded, and this caused congestion for streams that were routed through these hosts. This was not a problem for individual smaller HTTP requests. The delay or retry of these requests left users relatively unaffected. But for live streams, this caused buffering for individual streams, and this had a big effect on the viewers. This caused a side event, or what we call a SEV. Another example of this type of issue is when there is a fiber cut event. This is when there is an interruption to the physical fiber optic link. At our scale, these types of events are unavoidable and happen on a regular basis. In many cases, a fast reconvergence algorithm is used, but this can't be used in all cases because of the scale at which we operate and the variety of use cases that we support. So in many cases, an event like this can cause a disruption that may last a minute or more, affecting all of the thousands of streams transiting that link. So a couple of years ago, we were experiencing these types of fiber cuts, on a weekly basis, and sometimes even a daily basis. And so we were in a position where we absolutely had to do something about this. And this was actually one of the big motivations for this project. With this system with the older system, each of the components in a single network path must be perfectly reliable and performant over the course of an entire 8-hour stream. However, with the nature of large-scale distributed systems, squeezing more reliability out of individual components in such a system is a fool's errand. We needed a different approach. We thought redundancy would be necessary. With each of the software components on each end of the link within our control, and a series of network and backbone issues affecting our reliability goals, we saw an opportunity to tackle this problem and have a big impact on live stream infra at Meta. So, let me hand it over to Jordi to talk about our solution to this problem.
Thanks a lot, Thomas. So, first of all, let me introduce briefly myself. My name is Jordi Cenzano. I joined Meta 3 years ago, and I'm really, really passionate about video. All my life, I've been working in video and media-related projects, and I started in the broadcast world a lot of years ago, probably too many years ago, and 10 years, more or less around 10 years ago, I transitioned to online video. And here I am at Meta, working with Thomas and in this project. So now let me talk about the requirements and constraints of this project. So the first one is that we wanted to reuse as much as possible the current technology we have at Meta. We didn't want to reinvent the wheel. The second one is simplification. This has always been, and it's always a big priority for us. So simple systems are more reliable. And finally, be flexible. So here at Meta, we have a lot of different use cases. And some streams requires a big reliability, and others, for instance, they care more about latency. So we have to have these knobs or levers available to us. Before presenting what we implemented, let me introduce the two main technologies we use. The first of all is Rush. This is a homegrown live streaming protocol. It's like a packager and a transport specification at the same time. So the main idea for Rush in this project is to replace RTMP and FLP. And as Thomas mentioned, this Rush is already used in our first-party apps today in production. And this gives us a lot of confidence in this protocol and in this solution. Also, more details about Rush. It's a Rush transport. It can work on top of TCP and quick streams in this case. Today in Meta, we are using it only on top of Quick. And we built it a few years ago here, and if you want to know more about it, we just published an IETF draft. And also there is an awesome talk by one of our colleagues, Kirill, that he gave in this same conference in 2020. So you can probably find it online. The second main technology that we have used is OIL. OIL stands for Output Input Language. And OIL gives us a very flexible way to store data in a distributed world. That means we can configure per file or per stream, this is very important, what we want to prioritize. This stream is very popular, so we want more reliability. This stream requires very low latency, etc. So in our use case, we are using OIL to write data from a POP to a data center in a highly reliable and low latency way, having those knobs in our hands. So as you can see in the block diagram, the writer writes at the same time the same data to two different data centers, but only waits for one acknowledgement. And then the reader is subscribed and reading at the same time from the two data centers and returns the read when the first chunk is available in either one of those data centers. This gives us the reliability that we wanted. If you want to know more about OIL, there is also an awesome talk from another of our colleagues, David Zhang, that gave in this conference on 2020. Now, let's see a few implementation details. To simplify the rest of the project, we first wanted to tackle the fragmentation problem. So, as you can see in the block diagram, we are ingesting two different protocols, RASH and RTMPS. And it seems a little bit problematic to have to handle all of these two protocols in every piece of our pipeline. And this is what we were doing. So basically, as part of this project, and also to simplify our whole infrastructure, what we decided is to translate RTMPS into RASH inside of our POPs. So now, all of our pipeline, except the POPs, only handles a single protocol. So with that, we were able to remove almost half of our code, creating a huge simplification in our infrastructure. The next step was to use HTTP chunks instead of streams, instead of TCP or quick streams, to write data from the POPs to the data center. This allows us to retry the whole chunk in front of network glitches or network problems. That makes the system much more deterministic, and since we read and write data based on offsets, we will never lose a piece of data. The price to pay for that, it's a little bit of overhead. But remember, we are talking about backbone networks here. So basically, bandwidth shouldn't be a big problem. And then our implementation makes the chunks size, so basically the write size, configurable. So that means that streams that cares a lot about latency, we can write every frame. That means that the latency, we don't have to wait until buffer a few frames. For streams that they don't care as much about latency, we can write 10, 20 frames, go, and then reduce the CPU consumption, the IOPS in our system. But to be honest, we did not add a lot here. Why? Because TCP and QuickStream already implement retries at packet level. And this is clearly not helpful in case of one link is congested or one link is down. But the important point here is that this feature enables the next thing that we are going to explain. Finally, we added all together. So we added OIL technology that allowed us to do parallel writes to the data center, following different network paths. So as you can see in the block diagram, the reader is subscribed to two different data centers. So now it's able to get the next frame as soon as it arrives to any of those data centers. And the writer writes the same data in parallel to two different data centers. So also, this allows us to stop and resume reading from any point, since now the ingest data is stored in a reliable and distributed storage. For the people familiar with Broadcast Wall, so we basically implemented SMPTE 2022-7 in the application layer. Finally, at least in my part, let me show you some results of this project. So the next graph shows you reliability data from a network event that we suffered a few months ago. As you can see in the purple line, there is a very, very big reliability dip. That means that during that network event, a lot of live streams disconnected or suffered buffering at that point in time. But can you see the orange line? Hopefully not. So the orange line are the number of streams affected by the same problems, so disconnections or buffering, that we were using this project. So we call internally a reliable live ingest. As you can see, those streams were not affected. So it seems that this worked. Let me show you a couple of numbers more about this project. So we measure the impact of a relay over millions of streams, and those were the main data points. So we were able to reduce by more than 40%, in some cases much more, the streams impacted by a problem in our infrastructure. So now our streams they are overall more reliable. And obviously this translated to better user experience. So a good metric to show that is that we were able to increase the time between rebuffers, playback rebuffers, so basically the time between the viewer sees the spinning wheel. So, sorry, not reducing, increasing the time between the viewer sees the spinning wheel by 6%. And this, at our scale, I think they are quite meaningful numbers. So, okay, now finally Thomas is going to explain some learnings that we got building this project.
Thanks a lot, Jordi. And now I want to share some of the learnings and conclusions from this project. The first one, live streaming is hard. The constraints of live video, high bandwidth, low latency, individually important requests, are a challenge for any type of infrastructure. With our old approach, all elements in the pipeline needed to be perfect during the length of a stream, but not so with the new approach. We showed that implementing redundancy for reliability had a real impact for our users. However, we learned that there is a trade-off to consider. In our case, if we want low latency, we need to issue a write for every single frame, and that means high overhead, high IOPS, and so high CPU. And last but not least, we need simplicity and a clear contract. This is key when you work with big teams and big systems where it is almost impossible to know every piece of the code. Make it simple and intuitive where possible. So, thanks a lot for listening. I hope you're enjoying this conference. Please don't hesitate to ask any questions in the Q&A after this talk. And also feel free to reach out to either of us afterwards via email or on Facebook. Thanks.